Hello guys and welcome to my YouTube channel. In this video I am going to explain embedded memory sections including .text, .data, .bss, stack and heap. When we write embedded C code, the program does not become one simple block of memory. Behind the scenes, the compiler and linker organize the firmware into separate memory sections. Each section has a different purpose, and each one affects how much flash and RAM the microcontroller will use. The .text section usually contains the program code. This is where the compiled machine instructions live. The .data section contains global and static variables that already have initial values. The .base section contains global and static variables that start at 0. The stack is used automatically for function calls, local variables, return addresses, and temporary data. The heap is used when the program requests memory dynamically during runtime, for example with malloc and free. In embedded systems, this topic is very important because memory is limited. A small microcontroller may have only a few kilobytes of RAM. If we do not understand where variables are stored, we can easily waste memory, overflow the stack, or create unstable firmware. Before we go section by section, let's first understand the general memory map. In a typical embedded system, memory is arranged using addresses. Low addresses are usually shown at the bottom, and high addresses are usually shown at the top. The exact layout depends on the microcontroller, compiler, linker, script, and toolchain, but the general idea is very similar across many embedded projects. At the bottom, we often have the program code area, such as .text. This is usually stored in flash memory, because the program must remain available even after power is removed. Above that, we usually have data sections, such as .data and .bss. These are related to global and static variables that live in RAM while the program is running. Then we have the heap. The heap is used for dynamic memory allocation, and it usually grows upward when new memory blocks are allocated. At the top, we have the stack. The stack is used for function calls and local variables, and it usually grows downward. Between the heap and the stack, there is free space. This free space is extremely important. If the heap grows too much, or if the stack grows too much, they can move toward each other. If the stack and heap collide, the firmware can behave unpredictably. It may crash, corrupt variables, or fail in a way that is very difficult to debug. That is why embedded developers always need to understand the memory layout, not only the code logic. The .text section is where the actual program code is stored. When we write a function in C, the compiler converts that function into machine instructions. Those instructions are what the processor actually executes. All of that compiled instruction code usually goes into the .text section. For example, if we write a function to toggle an LED, the C code is converted into CPU instructions that access a hardware register. Those instructions are placed in .text. In most embedded systems, .text is stored in flash or ROM. This is important because flash memory is non-volatile. That means when power is removed, that the program is not lost. When the device turns on again, that the processor can still fetch and execute the firmware. The .text section is usually read only during runtime. The processor reads instructions from this section, but the program does not normally modify it while running. This section can contain startup code, the main function, interrupt service routines, driver functions, and application logic. Sometimes, depending on the compiler and linker, read-only constants may also be stored near this area, or in a related section like .data. One practical point is flash usage. If the .text section becomes too large, the firmware will not fit into the microcontroller flash memory. So when your build output says flash usage is high, the .text section is one of the first areas you should check. The .data section is used for global and static variables that have explicit initial values. For example, if we write int speed equals 10, this variable already has a value before the program starts. When main begins, speed must already contain 10. But here's the important embedded detail. At runtime, this variable lives in RAM, because the program may change it. But the initial value must be stored somewhere permanent, because RAM loses its contents after reset or power loss. So the initial value is stored in flash as part of the firmware image. Then during startup, before main runs, the startup code copies that initial value from flash into the .data section in RAM. This means .data can consume both flash and RAM. Flash stores the initial image, and RAM stores the runtime variable. Static variables with initial values also go into .data. For example, static uint 8 tmode equals 1 also needs to be initialized before the program starts. This is why large initialized global arrays can be dangerous in small embedded systems. They may increase flash usage and RAM usage at the same time. For example, if you create a large lookup table as a normal initialized global array, it may occupy RAM even if the values never change. So the .data section is useful, but it must be managed carefully. In embedded systems, every byte of RAM matters. The .bss section is used for global and static variables that start at 0. For example, if we write int error count without assigning an initial value, that variable usually goes into .bss. The same is true for static buffers, counters, flags, and state variables that do not have explicit initialization. .bss variables still occupy RAM. This is very important. .bss is not free memory. If you create a large receive buffer in .bss, it still reduces the available RAM in your system. The difference between .data and .bss is how the initial value is prepared. .data needs real initial values copied from flash to RAM. .bss does not need those values stored in flash. Instead, the startup code simply clears the whole .bss region to 0 before main starts. So .data is copied from flash, while .bss is 0 filled during startup. This makes .bss efficient for variables that only need to start from 0. Common examples include error counters, ready flags, communication buffers, sensor state variables, and status flags. But we still need to be careful. If we create too many large global buffers, .bss can become huge and consume most of the RAM before the program even starts. When debugging memory problems, always check .data and .bss together, because both sections use RAM. The stack is used automatically by the program when functions are called. Every time a function runs, the system may store a return address, saved registers, function parameters, and local variables. This group of information is often called a stack frame. For example, if we have a function called foo, and inside that function we create int a equals 5, that local variable usually lives on the stack. If we create char buffer 32 inside the same function, that buffer also usually lives on the stack. The stack is fast because allocation is simple. The processor mainly adjusts the stack pointer when entering and leaving functions. The stack is also automatic. When the function starts, stack space is used. When the function returns, that stack space is released automatically. This is one reason embedded systems often prefer stack allocation for small temporary variables. But the stack has a serious risk: stack overflow. If the program has deep recursion, too many nested function calls, or large local arrays, the stack can grow too much. Since stack memory is limited, it can overwrite other memory areas and cause unpredictable behavior. This can be very dangerous because stack overflow does not always create a clear error message. The firmware may simply crash, reset, or behave strangely. A good embedded rule is simple: use the stack for small local variables, but avoid huge local arrays unless you know the stack size is safe. The heap is used for dynamic memory allocation. Dynamic allocation means the program asks for memory while it is already running. In C, this usually happens with functions like malloc, calloc, realloc, and free. For example, if we write char pointer buffer equals malloc64, the program asks the heap for 64 bytes at runtime. If the allocation succeeds, malloc returns a pointer to the allocated memory block. If it fails, malloc returns null. That is why embedded code must always check the returned pointer before using it. The heap is flexible because the size and lifetime of the memory can be decided at runtime. This can be useful when the program does not know in advance how much memory it will need, but in embedded systems, this flexibility comes with serious risks. One risk is fragmentation. Over time, the heap can become divided into allocated blocks, freed blocks, and small gaps. Even if the total free memory looks enough, there may not be one large continuous block available. Another risk is memory leaks. If the program allocates memory and forgets to free it, available RAM slowly decreases. Heap allocation can also have variable timing. Sometimes allocation is fast and sometimes it takes longer. In real-time systems, this lack of predictability can be a problem, so the heap is powerful, but in embedded firmware, it should be used very carefully. Now let's compare the stack and the heap directly. The stack is automatic. The compiler and processor manage it during function calls. When a function starts, stack memory is used. When the function exits, that memory is released automatically. The heap is dynamic. The program manually asks for memory using malloc or similar functions, and then the program must release that memory using free. The lifetime is also different. Stack variables usually exist only inside their function scope. When the function returns, those variables are gone. Heap memory can continue to exist even after the function that allocated it returns. It stays allocated until the program frees it. The stack is usually very fast and predictable. This makes it very useful in embedded systems, especially for small local variables and temporary data. The heap is more flexible but less predictable. It can suffer from fragmentation, allocation failure, memory leaks, and variable timing. The stack has the risk of stack overflow. The heap has the risk of fragmentation and leaks. In embedded development, predictability is often more important than flexibility. That is why many embedded projects prefer stack allocation, static allocation, or fixed size memory pools. The key point is not just whether the code works once. The key question is whether the code can run safely and reliably for hours, days, months, or even years. Many embedded projects avoid the heap because embedded systems need predictable memory behavior. The first reason is fragmentation. Imagine the heap as a row of memory blocks. After many allocations and frees, small gaps can appear between used blocks. These gaps may be too small for future allocations, so even if there is free memory available, it may not be usable for the next request. The second reason is non-deterministic timing. In real-time embedded systems, we often need to know how long an operation will take. Heap allocation can vary depending on the current state of memory. That makes timing harder to guarantee. The third reason is allocation failure. malloc can return null if there is not enough suitable memory. If the code does not check for null and continues using the pointer, the firmware may crash. The fourth reason is memory leaks. If memory is allocated but never freed, the system slowly loses RAM. This is especially dangerous for devices that must run continuously. The fifth reason is limited RAM. Many microcontrollers have very small memory budgets. Some systems only have a few kilobytes or tens of kilobytes of RAM. Because of these risks, embedded developers often prefer static allocation, stack allocation, or fixed size memory pools. These methods are usually easier to test, easier to analyze, and much better for predictable firmware behavior. Now let's finish with a complete example. Suppose we have a constant message, an initialized counter, an uninitialized flag, a local variable, and a buffer created with malloc. The program instructions themselves go into .text. This includes the compiled machine code for main, the loop, and any functions used by the program. The constant message, such as const-char message equals OK, may go into read-only memory, often flash or a read-only data section, depending on the compiler and linker. The initialized global variable, like int counter equals 3, goes into .data. Its initial value is stored in flash, and during startup, it is copied into RAM. The uninitialized global variable, like int flags, goes into .bss. It is placed in RAM and cleared to 0 before main begins. The local variable inside main, such as int local equals 7, usually goes on the stack. It exists while the function is active. The buffer created by malloc belongs to the heap. The pointer variable itself may be local, but the allocated memory block is on the heap. This example shows why memory sections matter. Two variables may look similar in C code, but they can live in completely different places in memory. The key takeaway is simple. Every variable lives somewhere specific based on lifetime, initialization, and purpose. When you understand this, you can write embedded firmware that is more efficient, more reliable, and much easier to debug. Thanks for watching this video, guys. Please share, like, and comment below. Also subscribe to my YouTube channel for more videos.